Let's discuss about junction field effect transistor, nothing but JFET. In the bipolar junction transistor tutorials, we saw that the output collector current of the transistor is directly proportional to the input current flowing into the base terminal of the device, thereby making the bipolar transistor a current operated device because a smaller current can be used to switch a larger load current. We have already discussed about the BJT in detail. So, let us now discuss the junction field effect transistor, that is JFET, its characteristics and its working. But primarily we must know what JFET is. So, coming to field effect transistors, so which is shortly known as FETs. So, these are usually termed as unipolar transistors because these FETs operations are involved with a single carrier type. The field effect transistors are categorized into different types such as MOSFET, JFET, DG MOSFET, FET, HIGFET, QFET and so on. But only MOSFETs, that is metal oxide semiconductor field effect transistors, and JFET junction field effect transistors are typically used in most of the applications. So, before discussing in detail about the junction field effect transistor, primarily we must know what is JFET. The field effect transistor is a 3-terminal unipolar semiconductor device that has very similar characteristics to that of BJT. For example, it has got high efficiency, instant operation, robust and inexpensive, and can be used in the most electronic circuit applications to replace their equivalent BJTs. Field effect transistors can be made much smaller than an equivalent BJT transistor, and along with their low power consumption and low power dissipation, this makes them ideal for use in integrated circuits such as the CMOS and the range of the digital logic chips. The field effect transistor, or simply FET, uses the voltage that is applied to the input terminal called the gate to control the current flowing through them, resulting in the output current being proportional to the input voltage. As their operation relies on any electric field generated by this input gate voltage, this then makes the field effect transistor a voltage operated device. In our previous tutorials BJT, we have seen that there are two basic types of bipolar junction transistor construction, which are NPN and PNP, which basically describes the physical arrangement of the P type and the N type semiconductor materials from which they are made. This is also true of FETs, as there are also two basic classification of FETs called the N channel FET and the P channel FET. The field effect transistor is a 3-terminal device that is constructed with no PN junctions within, the main current carrying the path between the drain and the source terminals. These terminals correspond in function to the collector and the emitter respectively of the bipolar transistor. The current path between these two terminals is called the channel, which may be made up of either P type or the N type semiconductor material. The control of the current flowing in this channel is achieved by varying the voltage which is applied to the gate. As their name implies, bipolar transistors are bipolar devices because they operate with both types of charge carriers, that is nothing but the holes and the electrons. The field effect transistor, on the other hand, is a unipolar device that depends only on the conduction of the electrons, which is in N channel, or it might be the conduction of the holes, which is in P channel. The field effect transistor has one more major advantage over its standard bipolar junction transistor cousins, in that their input impedance, that is Rin, is very high, that is it is thousands of ohm, while in the BJT it is comparatively low. This very high input impedance makes them very sensitive to the input voltage signals, but the price of this high sensitivity also means that they can be easily damaged by the static electricity. As we discussed earlier, the JFET is one type of FETs which is used as a switch and can be controlled electrically. Through the active channel, the electric energy will flow between the source terminal and the drain terminal. if the gate terminal is supplied with a reverse bias voltage, then the flow of the current will be completely switched off and the channel gets strained. The junction field effect transistor is generally classified into two types based on their polarities, and they are N-channel junction field effect transistor, that is N-channel JFET, and P-channel JFET. So let's look into the N-channel JFET. The JFET in which electrons are primarily composed as the charge carrier is termed as the N-channel JFET. Hence, if the transistor is turned on, then we can say that the current flow is primarily because of the movement of the electrons. When we look at the P-channel JFET, the JFET in which holes are primarily composed as the charge carrier is termed as the P-channel JFET. Hence, if the transistor is turned on, then we can say that the current flow is primarily because of the holes. Let's look at the working of the JFET. The operation of the JFET can be studied separately for both N channels and separately for the P channel. So let's now look at the N channel operation of JFET. The working of JFET can be explained by discussing about how to turn on the N channel JFET and how to turn off the N channel JFET. For turning on an N channel JFET, positive voltage of VDD has to be applied to the drain terminal of the transistor with respect to the terminal, that is with respect to the source terminal, such that the drain terminal must be appropriately more positive than the source terminal. Thus, the current flow is allowed through the drain to the source channel. If the voltage at the gate terminal, that is VGG, is 0 volts, then there will be maximum current at the drain terminal and N channel JFET is said to be in on condition. So let's look at the N channel operation of the JFET. For turning off the N channel JFET, the positive bias voltage can be turned off or a negative voltage can be applied to the gate terminal. Thus, by changing the polarity of the gate voltage, the drain current can be reduced and the N channel JFET is said to be in off condition. Let's look at the P channel operation of JFET. For turning on the P channel JFET, negative voltage can be applied across the drain terminal of the transistor with respect to the source terminal, such that the drain terminal must be appropriately more negative than the source terminal. Thus, the current flow is allowed through the drain to the source channel. If the voltage at the gate terminal VGG is 0 volts, then there will be maximum current at the drain terminal and the P channel JFET is said to be in the on condition. For turning off the P channel JFET, the negative bias voltage can be turned off or positive voltage can be applied to the gate terminal. If the gate terminal is given a positive voltage, then the drain current starts reducing and thus the P channel JFET is said to be in the off condition. Looking at the JFET characteristics, the JFET characteristics can be known for both N channel and the P channel. So let's now look at the N channel JFET characteristics. As seen in the N channel JFET characteristics or the transconductance curve, which is graphed between the drain current and the gate source voltage, there are multiple regions in which the conductance curve and they are ohmic, saturation, cutoff and breakdown regions. N channel JFET characteristics. The ohmic region is the only region in which the transconductance curve shows linear response and the drain current is opposed by the JFET transistor resistance. Saturation region. In the saturation region, the N channel junction field effect transistor is in the on condition and active as maximum current flows because of the gate source voltage which is being applied. Cutoff region. In this region, there will be no drain current flowing and thus the N channel JFET is in off condition. The last is the breakdown region. If the VDD voltage applied to the drain terminal exceeds the maximum necessary voltage, then the transistor fails to resist the current and thus the current flows from the drain terminal to the source terminal. Hence, the transistor enters into the breakdown region. P channel JFET characteristics. In the P channel JFET characteristics or the transconductance curve, which is graphed between the drain current and the gate source voltage, there are multiple regions in the transconductance curve and they are ohmic, saturation, cutoff and the breakdown regions. So, looking at the P channel JFET characteristics, the first region is ohmic region, the only region in which transconductance curve shows a linear response, and the drain current is opposed by the JFET transistor resistance, which is termed as the ohmic region. Saturation region. In this N channel JFET, the saturation region is in the on condition and active as the maximum current flows because of the gate source voltage which is being applied. Cutoff region. In this region, there will be no drain current flowing, and thus the N channel JFET is in off condition. Breakdown region. If the VDD voltage applied to the drain terminal exceeds the maximum necessary voltage, then the transistor fails to resist the current, and thus the current will flow from the drain terminal to the source terminal. Hence, the transistor enters into the breakdown region. Let's now look at the JFET applications. JFET is used as a switch, chopper to chopper, that is nothing but a DC to DC converter. These are used as amplifiers, used in buffers. Because of its low frequency drift, JFETs are used in the oscillatory circuits. These are used in the digital circuits such as computers, LCD and memory circuits because of their smaller size. These are used in communication equipment such as FM and TV receivers because of their low modulation distortion. These are used as voltage control resistors in the op-amps. These are also used in cascade amplifiers and in RF amplifiers. Let's now look at the difference between the BJT and the FET. BJTs are current controlled, whereas FETs are voltage controlled. BJTs offer smaller input impedance, FETs offer greater input impedance than the BJTs. BJTs offer greater gain at the output than the FETs. The gain of the FETs are smaller than that of the BJTs. BJTs are larger in size and therefore take up more physical space than the FETs normally. FETs can be manufactured much smaller than the BJTs. This is especially important for integrated circuits that are composed up of many transistors. BJTs are inexpensive to manufacture, especially the MOSFETs are more expensive to manufacture. MOSFET. Let's look into the MOSFET. MOSFET, which stands for metal oxide semiconductor field effect transistor, is a semiconductor device which is widely used for switching and amplifying electronic signals in the electronic devices. The MOSFET is a core of the integrated circuit and it can be designed and fabricated in a single chip because of this very small sizes. The MOSFET is a 4-terminal device with source, gate, drain and body terminals. The body of the MOSFET is frequently connected to the source terminal, so making it a 3-terminal device like the FET. The MOSFET is very far the most common transistor and can be used in both analog as well as digital circuits. The MOSFET works by electronically varying the width of the channel along with the charge carrier's flow. That might be electrons or the holes. The charge carriers enter the channel at the source and exit via the drain. The width of the channel is controlled by the voltage on an electrode which is called as the gate, which is located between the source and the drain. It is insulated from the channel near an extremely thin layer of the metal oxide. The MOS capacity present in the device is the main part. The MOSFET types. There are 2 types, the depletion mode and the enhancement mode. Let's look at the depletion mode. When there is no voltage on the gate, the channel shows its maximum conductance. As the voltage on the gate is either positive or negative, the channel conductivity decreases. Looking at the enhancement mode, when there is no voltage on the gate, the device does not conduct. More is the voltage on the gate, the better the device can conduct. Let's look at the working principle of the MOSFET. The aim of the MOSFET is to be able to control the voltage and the current flow between the source and the drain. It works almost as a switch. The working of a MOSFET depends upon the MOS capacitor. The MOS capacitor is the main part of the MOSFET. the semiconductor surface at the oxide layer, which is located between the source and the drain terminal. It can be inverted from the P type to the N type by applying the positive or the negative gate voltages respectively. When we apply the positive gate voltage, the holes present under the oxide layer with a repulsive force and the holes are pushed downwards within the substrate. The depletion region populated by the bound negative charges which are associated with the acceptor atoms. The electrons rich channel is formed. The positive voltage also attracts electrons from the N plus source and the drain regions into the channel. Now, if a voltage is applied between the drain and the source, the current flows freely between the source and the drain, and the gate voltage controls the electrons in the channel. Instead of the positive voltage, if we apply a negative voltage, a hole channel will be formed under the oxide layer. Let's look at the P-channel MOSFET. The P-channel MOSFET has a P-channel region between the source and the drain. It is a 4-terminal device such as the gate, drain, source, body. The drain and the source are heavily doped P plus region and the body or the substrate is the N type. The flow of the current is positively charged holes. When we apply the negative gate voltage, the electrons present under the oxide layer which are pushed downwards into the substrate with a repulsive force. The depletion region populated by the bound positive charges which are associated with the donor atoms. The negative gate voltage also attracts holes from the P plus source and the drain region into the channel region. Looking at the N-channel MOSFET. The N-channel MOSFET has a N-channel region between the source and the drain. It is a 4-terminal device such as the gate, drain, source and body. In this type of MOSFET, the drain and the source are heavily doped N plus regions and the substrate or the body is a P type. The current flows due to the negatively charged electrons. When we apply the positive gate voltage, the holes present under the oxide layer is pushed downwards into the substrate with a repulsive force. The depletion region is populated by the bound negative charges which are associated with the acceptor atoms. The electrons reach the channel is formed. The positive voltage also attracts electrons from the N plus source and the drain regions into the N channel. Now, if a voltage is applied between the drain and the source, the current flows freely between the source and the drain, and the gate voltage controls the electrons in the channel. Instead of the positive voltage, if we apply a negative voltage, a hole channel will be formed under the oxide layer. For an example, using the MOSFET as a switch. In this circuit arrangement, an enhanced mode and an N-channel MOSFET is being used to switch a sample lamp on and off. The positive gate voltage is applied to the base of the transistor and the lamp is on, or at 0 voltage level the device turns off. That is nothing but VGS is 0. If the resistive load of the lamp was to be replaced by an inductive load and connected to the relay or the diode, which is the protection to the load, in this circuit it is very simple circuit for switching a resistive load such as a lamp or a LED. But when using MOSFET to switch either inductive load or a capacitive load, protection is required to contain the MOSFET device. We are not giving the protection to the MOSFET, the device will be damaged. For the MOSFET to operate as an analog switching device, it needs to be switched between its cutoff region where the VGS is 0 and the saturation region where its VGS is plus V.